So our problem statement today is the necklace is on a man's neck was analyzed. The forces of the cables were determined from the bottom of the pendant Z of each string that touches the side of his neck. What is the weight of the end? The end of the pendant resting on the man's neck at a 45-degree angle, and what would be the tension of the string and the normal force on the pendant. So as of right now, we have our YZ axis and we have our ZX axis here to show you the leaning. And we're going to assume that this side is actually nailed down as if it was a if it was pinned. So it's free moving, but it will stay in this direction. Some of our assumptions are going to be the string length, which is really irrelevant in this case. Cross, the mass of the cross or the pendant, which is going to be 2 grams. Neglect the weight given through the sides of the cross, and this is actually supposed to be 2 kilograms. Excuse me. And gravity we consider 9.81. Now, first things we need to do is draw it in the XZ plane. Okay, so you can see that it is attached to a string at the end of the wall, and then we put a pin there to show you where it will stay no matter what. Now we have to find the tension, and we need to find the reaction forces, like what the problem has asked. So we start off by finding the moments at a certain position A, which is right here at this pin. We can determine. We put the coefficient TBC to represent tension, and here we are representing the length of the system itself, minus the mg gravity, and half of that to tell you the weight of the plank itself, and its angle to better determine how the weight is distributed. So then we solve for our tension. After doing some algebraic simplifications, we will find out that TBC, not to be mistaken with these values, but we replace it with new values so we can determine it in the ZX axis. Okay, and then we go down here and we find our reaction forces at the pin A. So that at the pin we find the sum of the forces, which we know is equal to 0 because it is static. And then we solve our algebraic expression for that specific area, which we end up getting our reaction force at X at 4.905 newtons. And then we find the sum of the forces in the Y direction, AY plus TBC, more algebraic expressions, and we end up with 14.415 newtons. Now that we got this, we're good to go on these. These will be the answers for that. Now, we need to take our tension forces that we had put in this rope and transfer it to 2 ropes. Because the sum of the tensions of A, which is technically what we found here, will be determined now through BC, or now we've solved through BC. So we assume we grab our equation from paper 2. Now we translate it to the ZY axis and find our 2 different tensions. So we label our tension that we found on paper 1 at A for 6.937 newtons. Now we find the sum of the forces again, but in these new directions, which is now assuming X and Y. Okay, so in the Y direction, which is equal to 0, which we can determine by the tension A, and then the 2 new tensions here. So we know this tension, we can consider that a negative, and then we can consider these 2 tensions with the angle. We have to do a trigonometric expression so we can determine this angle in this direction, and the cosine direction in this case, and this force in the cosine direction. We do that here, and we set it equal to 0. And we do the same exact thing for f of x, and set it equal to 0. And now you can do 2 things. You can solve for each one through algebraic expressions, or you can plug it into a matrix, which is what I did, to find our two new tensions TB and TC. Now that we have found that, we have found our two tensions of our string, and we have found our reaction forces from the pendant leaning on the neck. And that resolves our problem.